Estão-me a ouvir? Oi? Um, dois? Ok. Então, sorry, switching to English, yes. Yeah, welcome to this talk. So, are gonna get started with blockchain. So for that, we will kind of go a bit first on the goals. So we will go over some blockchain concepts, of course. First, who here has blockchain? Crypto, tokens, digital assets, NFTs? Hands in the air. Okay, okay. A friendly crowd, I'm saying. Okay, let's go. So we'll go also over some blockchain context, specifically targeted at the practical side, okay? And then our end goal is to create a custody service. What is a custody service? Basically, it's a service, right, that holds our cryptographic material for us and allows us to do the operations that we want to do on the blockchain. So this is basically your app that you use on your mobile, your extension on your browser, for example, MetaMask. Basically, we are going to do that, but in a way that we can, for example, an example is building a custody, or sorry, an exchange service, for example, a Binance, a Coinbase. All of them do what we are going to do here. We are going to see just a tiny bit, but yeah, so the major features will be, we will do withdrawals, so moving money out of our system into an external account. We will do deposits, so detecting money coming into our system to one account within our system. And of course, we need to see the balance just for the sake of knowing how much money we have. But yeah, first, a little bit about me. My name is Gonçalo Pereira. I'm here from Coimbra. I've been a backend engineer for over 8 years, and I've been mainly involved in the business critical markets, always with a ton of security involved. And since 2001, since last year, I joined Anchorage Digital, and I started working with blockchain and digital assets. Digital assets here, it's everything associated with blockchain. Can be a cryptocurrency, can be a token, but it can also be, for example, an non-fungible asset, an NFT. There's a whole array of stuff. So, but yeah, let's go into it. So let's start first for those of here that are not really, oh, by the way, as we go, mainly on even more on the code side, feel free to raise your hand and make questions so that we can all go the same pace, go the same, and understand what we are here. Hopefully, I'm good at giving my message across. So yeah, let's go blockchain. So reducing it bare minimum, blockchain is a word conjunction, right? The grouping of the words block and chain. Okay, what does this mean? So this means that it's a chain of blocks. Each block will have transactions within it. Okay, these transactions can be what we normally identify as a transaction, so moving funds, but they can also be, in the case, for example, of Ethereum and other similar blockchains, it can also be, for example, executing code on a smart contract on the blockchain, or deploying a new smart code, a smart contract, sorry. And these blocks form a chain because each block kind of points to the previous block, all the way until we reach the first block, the Genesis block, okay? It's the name that they called the first block of all. And for example, in the case of Ethereum, this block was created on the 30th of July, 2015, okay? And a new block, in the case of Ethereum again, has been added more or less 13, 14 minutes, every single 13, 14 minutes, a new block has been added. So now we are, yeah, up to a big number. And as the time flies, we get new blocks added. So this is the main gist of blockchain. Here, the transactions that happen in the blocks can be, again, what we normally identify as a transaction, right? So moving funds, for example, 1.01 Ethereum, to some other address. Can also be, for example, executing a function X with parameters Y on a contract located at a certain address. And of course, can be the deployment of that address. So, okay. Another part to blockchain is the network effect. It's actually what creates the decentralization properties of blockchain. So blockchain is a distributed network. Again, very basic stuff. It is composed by a lot of clients. These clients have to implement a certain protocol, for example, the Ethereum protocol. And they can be both developed by the Ethereum Foundation, for example, the team behind the Ethereum project, or can be by other team as well as long as they follow the spec. And naturally, these blocks are connected, right, to each other, so they discover and communicate between themselves. And what do they communicate for? Achieve consensus, agree on the blockchain state. Each and every single one of them will have a copy of the blockchain. There is no single source of truth. Okay, there's also it's where the decentralization comes from, and they must run an algorithm in order to agree on we can say the network state. Okay, so the majority of the nodes, the majority or the state of the majority of the nodes wins the state overall, and they agree. And this will be important as we will see implementing our custody service. Okay, understanding if a transaction went successful or not. So yeah, but let's go to brief introduction. The goal is just to introduce some concepts, just for you not to be listening to me saying strange words. So yeah, so our goal will be to implement a service, again, a custody service that can do the withdraw, deposit, and check balance. So going a bit more specifically, we call it withdraw because we are sending funds from an internal address, an account internal to our system, to an account outside of our system. And deposit the other way around, outside to inside. And then, of course, the balance, we need to make sense of everything that is happening on the blockchain. So yeah, let's go into a practical example. So we want to build a custody service, but in order to build such a custody service, we will need to interact with the blockchain. Okay, so we need a gateway to interact with the blockchain, and it will be exactly one of these nodes. We need to run our own node. We could also use a public node, but again, as in software, using something of a third party, we are dependent on that third party. So we want to. Okay. Oh, okay. So yeah, to build our own, let's go. I've already prepared here a kind of a setup. So I have here a Docker file. Can you see? Yeah, can see. Yeah. So I've built here a Docker file. So basically, this is piggybacking on top of the official image by the Ethereum community, the Ethereum Foundation. So I'm going off the main Ethereum client and building my stuff. Here, important stuff. So I'm making a local network, okay? I'm not connecting to the main network. So I'm having my own Ethereum network. I can have how much or whatever much Ethereum I want in this specific network. And so to do that, to build that first block, that Genesis block, essentially we have to create this file, this Genesis JSON file. And what we are saying here is we are giving a ton of configurations. One important one, the one on top, the chain ID, is like an identifier of our particular chain. This is more like to avoid us from sending a transaction to the Ethereum mainnet, which was targeted at some other mainnet or some other network compatible with that Ethereum mainnet. For example, I don't know, the Binance Smart Chain is an example of a Ethereum copy. So yeah, we want a specific one. I just made up this number. And another thing that I've configured here is a first allocation of address. So from the start, these three addresses will have a certain amount of Ethereum. Okay, this is Ethereum has 18 decimals, so if you exclude the 18 zeros, believe me, that's 18, we get on one account 1 Ethereum, okay? On another, we get 999. Okay, yeah, sure. Let's run our node and see and check it out. Let's see how. Oh, by the way, I have a Docker Compose here just to make things tidy. Here, we have our port that we will use. We will use a HTTP JSON RPC interface, okay, to connect to our node to interact with it. So I'm here exposing that port, 8545. So running it, I'm just building it for the sake of it. We can see that it is indeed running. And if we look at our container, we can see that we are doing a ton of stuff here. A ton of stuff is happening here. So mainly, what is happening, you can already identify a nice phrase, mined potential block. So our network is both providing the gateway into or this node is both providing the gateway into my local blockchain network, as well as mining new blocks, okay? So of course, this is just for local purposes, local development purposes, not an actual blockchain for production purposes. But here, we can see that we are constantly mining blocks. So we are seeing we mine the number 10, now 11, 12, 13. So each 5 seconds we are mining a new block, okay? And we will see whenever we send transactions, they will appear here and they will be included into a block. Again, following the full blockchain as it grows, and we will naturally interact with this. So yeah, we have our node running. One thing that we can do, for example, is we can use, for example, here MetaMask. Who here knows, has interacted, used MetaMask? Yeah, a ton of people, right? Pretty wide adoption of MetaMask. So here I'm connecting specifically to my network. Just to, I've set up here some accounts, and let me just make sure that I reset the account information on MetaMask, just to make sure that it is indeed connecting to my new instance, and it has already picked up the balances. So 1 ETH on the account starting 59, and we have 999 on the account started with B4. Okay, so we have balance. Everything is okay. We have a wallet that we already know that it is working and it's fully functional, is detecting the balances, and will also detect the transactions happening on the network. So basically, we are gonna build our service to do mostly the same thing that is happening here. Okay? Any questions so far? No? Okay. I'm gonna assume that we are going okay. Yeah, so let's go into the actually building our service. So again, in order to do that, we will need to connect to our client. We will do that using an HTTP Rpc JSON interface. That interface is specified by the Ethereum Foundation. It's the actual protocol, one of the parts of the specification of these clients, and this is the Rpc specification that we are going to use. For example, we can see some stuff here. For example, this one, ETH chain ID to get that chain ID. We can get, for example, one here. We are interested in creating a transaction, so we can see here the send draw transaction. Okay, so we send here a string of X encoded bytes, okay, and we send it to the network. And we will use some other parameters here, but we will discuss them as some other methods here, but we will discuss them as we go building our service. So yeah, let's go into code. I've set up here a Quarkus application, okay, a very standard Quarkus application. Let's look into the POM file. So basically, okay, we are here using Java 11, going for one of the pretty recent version of Quarkus. And the most interesting part here is this dependency, so the Web3J dependency. Okay, this is our dependency that will wrap these endpoints. It will handle encoding, decoding. It's like, for example, JAX-B, for example, or Jackson. So it will handle that part, plus knowing the endpoints, knowing how to invoke them, and so forth. So will do a lot of heavy lifting for us. And also, for example, handle things like signing the message, building a message. We will see. So we have that. We have here a ton of stuff that I've built some example repositories. They are holding data in memory, but imagine that they would go to the database doing things properly, of course. But going into our specific case, so we want to build the withdraw function first. So again, going back to it, a withdraw function is sending a transaction from one of our accounts into an external account. Okay? So we want to build a transaction where we say, okay, from this address, we send money into that address. Here, of course, we are reducing it to sending money, but could be a smart contract invocation. Okay? So to do that, I've built here an endpoint. Imagine that this would be a REST endpoint here with /operations. Okay, if we do a post, we are creating a new operation. Doesn't really make sense to create deposit operations because they come from the outside. So we are creating a withdraw operation. And here on our model, we are getting an amount, a recipient, of course, it's to whom we will send the funds. And we also have here a sender. The sender would be the account associated with the user logged into our service. Here we are kind of just cutting corners and sending it right away in the payload. So we are specifying the sender. The sender is sending this amount to this recipient. Okay. So starting first, let's just do first some sanitization, just because, for example, the addresses in Ethereum, they can be mixed case, okay? So addresses, I don't know if you have looked at an address. I can show you here. For example, this would be an address, okay? This would be one of our addresses. So they can have mixed case, as you can see. And the purpose of this is for checksum purposes. When we are writing the address, by like copying or something, it makes sure that we do not make mistakes. At least picks up a certain degree of mistakes. So in order to kind of forget that and make sure that our matches are correct, we are going to do just a lowercase. So this is our sender address. So let's do the same thing for the recipient. Lowercase, and we will say, okay, a recipient. Okay, and let's also extract the amount right away and say that this is a string. So let's go and pull it into a big integer. As you saw, the precision in Ethereum has at least 18 decimal cases. So yeah, gets pretty big, the values. And here, okay, let's just rename this to amount. Okay, so we have sanitized our addresses. Naturally, here we would do a ton of stuff. For example, validating that the user sending the amount has enough money to send that amount. Otherwise, it will simply fail on chain, on the blockchain. Other stuff would be, for example, okay, checking if this address is correct, checking if the receipt is correct. So we would need to do a lot of validations. But at a certain point, we would reach actually building the transaction. So here, it's one part where Web3J kind of leverages and helps us out. So we can have here a class that you can just create here a static method, create Ether transaction. And we have a ton of parameters here. So first we have a chain ID, again, to make sure that we are targeting our correct network and not a test network or whatever. So we'll also have announce. We will go over what this is in a minute. We have our gas limit. The gas limit for, this is things specific to Ethereum, but the gas limit here will always be the same value because we are sending ETH transactions, so we can just use a constant here. And we will, of course, say where to. We are sending this. We want the recipient, and we will also want the value, which is our amount that we have pulled before. And then we have here two parameters. I will explain what this is. So this is a big and important mechanism in blockchain, which are the fees that you pay to send the transactions. So let's go and say, call it tip fee, and call this one max fee. Okay, so yeah, we have a ton of stuff to calculate before we create this transaction. So let's start maybe with the first, the announce. Okay, the announce is a mechanism for protecting against entry replay. So this is a number, a counter, which is capped on the blockchain, okay? And is incremented as we send new transactions. So this makes sure that if we try to send the same transaction twice, or two transactions with the same announce, one of them will be rejected. So it's just a protection parameter. Again, using Web3j, we want to go into the blockchain to fetch that data. We would use this example, this one here, get transaction count. So we want to send the address, and we want this is a parameter which allows us to kind of configure what exactly we want the transaction count from where we want them. We will actually want every single transaction count, so we will use a value here, the pending value. I've already done this here, but let's just get transaction count. So we would say, okay, we want the transaction count from the sender, the party sending the transaction. And we would say, okay, default parameter name, we would use the value pending, okay? I've already done here a utility method for that, which is here, compute account nonce. So basically, yeah, we are doing the same thing. Get transaction count, we are saying the address, and always pending. So let's just call that compute account nonce. Okay, we want the sender, and that's it. So one part, done. So now we enter a bit of a complex land. We enter the area of fees in blockchain. So fees in blockchain are very important because as the network is a decentralized network and a trustless network, it really doesn't control who is sending the transaction. If it is an authorized party, good intentions party, whatever. And so in order, for example, to protect against denial of service attacks, like people just spamming tons of transactions into the network just to bottleneck the network, we kind of have a mechanism where we have to pay for each transaction sent to the network, okay? We are paying, in this case, we call it gas, but it translates back to Ethereum. It's actually Ethereum. We are paying Ethereum, and we have to have the transaction being broadcasted, being accepted to the network. And here, these fees have an interesting mechanism. So it has changed at least, I would say, 2 times or 3 times. Slightly now, a big change in the middle of last year. And we have 3 parts to the fee mechanism. We have a base fee, we have a tip fee, and we have a max fee. Again, this is specific to the Ethereum blockchain, but other mechanisms similar to this one occur on other blockchains. Okay, it's always you have to pay in order to send transactions. The way you calculate it might be different. So we have a base fee. The base fee is always changing. It is the parameter which responds to network congestion. So it increases if the last block was very full. It decreases if the last block was almost empty. So it's kind of always shifting. So we have to account for it, and in order to account for it, where do we go fetch that data? From the blockchain. Okay, and again, we leverage our library, of course, to go, and we have here the gas price. This is a bit of a legacy name. Okay, this was changed in the last year. There's a bit of a legacy name. So we go fetch this gas price. It will actually be the base fee of the last known block. So we call it, and we have here. By the way, I haven't yet explained this. So this library has a mechanism where it can do both synchronous requests or asynchronous requests, and you can leverage reactive patterns on top of it. Here, for simplicity, I'm just using the synchronous, so it will be block on this send call, and it will only unblock when the client replies back to our request. And sorry, any question? No, okay. So yeah, so we get this base fee. Let's just call it a better name. Oh, it's a request. Let's give it like that. And we have to check if because of the way this library works, we have to check if we have errors. If we have errors, handle. Yeah, sure. Let's just postpone it. Yeah, it will be handled to the next developer coming in. And okay, sure, we have our gas price. Here we get the gas price, comes as a big integer, and we say, okay, this is the base, let's call it properly, the base fee. This is the base fee, okay? Again, this base fee is changing almost in each and every single block. And so we want to have here also an incentive for the people creating, or they call it in Ethereum right now, miners. Like it's the whole spending energy to validate blockchain now and how it's bad for the environment and whatever narrative. And here, what we are paying to those miners, the incentive for them to mine our block, to include our block over others, is a tip. Okay, kind of like the waiter in the United States where we pay the fee. So in order to compute that fee, for example, we could use whatever method we could think of. But here, for example, let's use the base fee. Okay, let's convert it to big decimal just for the sake of doing divisions and multiplications. And let's multiply it here for, I've already created here a constant 0.1, so 10% of the base value. So we are always paying proportionally to the base value. It's not a great approach, but yeah. And this will, of course, maybe do, so like we may just to make sure that we do not create here and we to big integration. Yeah, that's it. And okay, so tip fee, that's it. So we are calculating 10% of our base fee, okay, and making sure that we are always paying that. But again, one thing kind of can left us thinking here, because if this base fee is always changing, and if, for example, we do not specify enough tip fee, our transaction might be just delayed, and when it is added, we will pay, like, I don't know, for example, a ton of money to include our transaction. So we kind of, it's always good to have a capping portion to it. So the capping portion is like the max overall that we are willing to pay. Okay, and in order to calculate that, you are already kind of figuring this out, right? It's the base fee is always changing. The tip fee is on top of that. So we will allow some degree of variation on the base fee, add it the tip fee, and that's the overall maximum. Let's say the reasonable value is for it the base fee to like double. Okay, let's say it's okay for them to double. We are willing to pay that. So we have the tip fee, and given this, we have our max fee, the thing that we are willing to pay for this transaction. Okay, I've used the same names, so all of them have already plugged nicely into our raw transaction. Another part is we want to broadcast that transaction. Okay, if we did things just this way, nothing is really protecting our, nothing is really identifying us as the owner of this account, this address. So everyone could simply build this transaction, broadcast it on a random client, and be accepted. So we have to build another layer, build an additional security layer on top of our transaction, which is signing it. Okay, I'm sure that the people that has already used blockchain so far knows that things are signed and you have to keep your keys private, and that's the way that things are secure. Here, this is a bit of a big no-no to do, but here I've just placed my private keys here on this file. Feel free to grab them and use them, whatever. I just generated a random accounts. So, but just for the sake of being simple, I've here detailed my wallets, the address, the initial balance, which matches our Genesis JSON configuration file and our initial block, and the private key, of course. And so going into the signing part of the transaction, so we have to load these credentials. We have to load this private key. So let's load the credentials. So again here, basically this is just from that string creating an elliptic curve pair. So Ethereum uses elliptic curve key pairs, and with this utility, we can create the credentials from our key pair. We will have to fetch that data, so we can. I've built here a wallet repository. Basically, it loads that application properties file and just saves it into a map in memory. And so we do get wallet, the sender wallet, of course, and we have here our wallet. This is an optional, so we would need to check if it is empty, okay, if it is, handle, whatever, okay. And if we do handle, if we do have the wallet, we can then extract that private key. So we do get, and we do get private key, and it will create our credentials for us, okay. We can just inspect here, see, EC private key pair, create from that private key. Pretty standard cryptography stuff. So just a utility method that Web3j gives us. So again, we have the credentials, we have our transaction, we have to sign it, remembering signing. We have to sign our transaction. And to sign the transaction, again, Web3j, the RESCO, it gives us some transaction encoder utils here, and we can just say, okay, sign my message, give it the raw transaction, and of course, here's the credentials. Sign it for me. And here it goes. Some bytes come out. So this is the signed transaction. You can say bytes. Okay. And we have our transaction signed. So it's ready to be sent. Actually, it's not ready because here on the send raw transaction, it requests a string of encoded bytes. So yeah, we have to put it into X encoding. Okay. So Here you could use whatever. Here I'm using what Web3j also provides, and so this is the actual signed transaction. So this is the actual signed transaction. It's the one that we can send. Again, let's use the endpoint. Let's call it, send it, and send transaction, raw transaction, and that's the signed transaction. Oh, here I need to do the same thing, send, and then var. And that's it. So we have here our response. As we did countless times now, we have to verify if it has an error. If it has, let's handle it, whatever. Okay, so given this, what we already have is a submitted transaction. But here, let's first register inside our service. Let's just first, okay, so we create. I have already here all these beans created, and we have a ton of stuff here to fill. So the transaction ID, it will be the returned by this response, get transaction hash. We will have here the state. So the state will be, we have two states. Let's first fill in the rest, and then I will piggyback off that. So we have the sender, we have the recipient. Again, it's just filling in our stuff here. The type will be, we will have two operation types, withdraw and deposit. So we want the withdraw, definitely. And submit that, so we can just say, yeah, no. And that's about, oh, we are missing the amount. Here we are, I don't know why I put the string instead of the big integer, but yeah. So if I'm not missing anything, we are only missing the state, if I'm recalling correctly. So the state here, it's another layer of complexity, mainly driven by the distributed nature of the blockchain. So the state, when we send a transaction into the network, it might be successful or it might fail. So there is no guarantee that the transaction we send to the blockchain is successful. One way it can go wrong is the fee. We not paying enough for the transaction to be included. And if we do not do that, the transaction will simply hold on, be stuck, trying to get into a block, and we will have to rebroadcast it, first increasing the fee, naturally, putting another nonce, and rebroadcasting it. We can also cancel the last one. It's sending a transaction with the amount of 0. But yeah, so we kind of have here a bit of a pickle, right? Our operation is in broadcasting state, but we have to make sure that it either fails or it either is successful. If it fails, we will have to potentially broadcast it again. So how do we do that? One way that we could do that is here we have one endpoint that gives us that information. So it's the receipt. Where is it? It's below here. So we specify the hash, okay, and it gives us the receipt information. This can either appear or like be returned, right? It responds successfully, but it can either contain something or nothing. And if it does not contain anything, it means that it wasn't yet included into a block. It wasn't yet included into the blockchain, okay? And for example, stuff that only appears in this information is, for example, the actual gas used and the effective gas price that we paid for that transaction. So we have to kind of go and get this object to know exactly how much we paid for that transaction. Otherwise, when we submit, we are just estimating. It will be from the base fee plus tip up until doubling the base fee plus tip. It's the max fee that we calculated previously. So we could use this get receipt that transaction received. The thing is, if you start thinking about it, this won't really scale, right? Because every single transaction that you submit to the network, you will need to be constantly pulling on the network, checking if the transaction was already included or not. Each and every single transaction that you submit. So yeah, not really scalable. We have to find another way to do it. And a way to do it, it's a common practice, and even it's translatable to a ton of blockchains. Of course, you might be thinking, why doesn't the client notifies us of a completed transaction, accepted transaction? We could do that, but the thing is, we would have to keep constantly telling the node, oh, these are the transactions that we are interested. If, for example, imagine that we manage the node in a Kubernetes. If we have to wipe out our state, for example, reboot it again and load the full blockchain again because something got corrupted or whatever, our backend would have to go and load every single hash that we are interested, every single transaction ID, transaction hash that we are interested into that node, so that that node can then report us back. And how about if that's the only node that we have? How about if we, because of this mechanism, we fail to notice some transaction, right? It's not like foolproof. A foolproof method is one that I've here added. And I was planning on doing this also live coding, but I took a wise decision to not to do it because I only have 8 minutes and 40 seconds. And here, so what we are doing this here is we are scanning the network, okay? What does that mean? So we are going to the network and fetching the last known block, last included block, okay? We are doing this using this Web3j block number. So it gives us what we call in blockchain the network height, the blockchain tip, the blockchain height, the block height. And that value will be, for example, here. Let's look at our node that is here, hard working mining blocks. So right now we are at the number 378. The block 378. It's like it's on the corner, the bottom. 379, 380. So we are constantly mining blocks. So we will get that value. And then here I'm initializing the application with a 0 value. And here what we will do is, okay, so we know that the last one that we have scanned is a 0. So we know now that we have 300 and whatever blocks. So we will go and ask each and every single block between those two ranges and get that block, okay? So here we are doing that while. So while comparing the block being scanned with the last tip height, last known block number, okay, while it's still less or equal. And we are going to scan the block. And to scan the block, we are going to, of course, get the block information. So get block by number. It gives us the information on the block. This includes, naturally, the transactions, a list of transactions, and us by having here a list of transactions. So here we have a list of transaction results. These transaction results will actually contain the transaction. So we have to look at each transaction within each of the blocks we are scanning. And to do that, again, I've already implemented this scan transaction. And for that scan transaction, we go into the object. We go and fetch that other information that we were talking. It could be an alternative, although a poorly scalable one. So we get the receipt. We have to compute exactly how much we use to pay for that transaction, right? So we get transaction receipt, we get the effective gas price. Here I'm just converting because it comes in eggs, so removing the 0x and then converting from base 16 into base 10. And we are also gonna get here the gas usage. So how much did you pay? It's the gas used times the price. Pretty straightforward, yeah? So this was the amount in Ethereum that we paid for this transaction. And of course, we have to process. So here I'm creating a temporary object. And so it's from this sender to this recipient, paying this fee with this hash, with this amount. Okay, so we know exactly, we have extracted the transaction data from the blockchain. And now we are at the point where we can decide, was this a withdrawal? Was this a deposit? How should we look at this? And here, that's exactly what we are doing. So we are going into our wallet repository, finding, okay, is the sender in our system? If it is, we are processing the withdrawal, so we update the balance, and we mark the transaction here as confirmed. So it will change state from broadcasting to confirmed. For the deposits, it's already here also implemented, so we just did both stuff with the same scanning stuff. So we are both confirming withdrawals, and we are also detecting the deposits, because a deposit is a transaction that the recipient is in our system. A withdrawal is a transaction that the sender is in our system. Here, since I have set up two accounts in our system, we are kind of going to get both a registration of a deposit and a withdrawal and a deposit. So, but let's check it out so I'm here running our Quarkus dev, just to make sure that, again, our node is already running fast, working. And here we can already see, oh, it already picked our blocks, so scanned 430 blocks. It didn't pick anything because we haven't done anything on our network. So now 2 blocks more, so it will just keep working at this. You can already see this is a lot more scalable because we are pulling at a constant rate, right? We are pulling at the rate acceptable to detect on a timely manner the new blocks being added. We don't have to pull faster if we have more users, which would not be the case if we went with a receipt approach. So let's see it working, right? I think I have a bit of time to see it work. So here we will send an operation given the B4 sender and the 59 recipient. I'm sending 100 ETH. So I can check here the operation. Here it's broadcasting. You already saw on the top submit a transaction. Oh, it's already running away. Here, submit a transaction. Okay, it got received, and then it got mined into a block here. So it went into the 442 block, the blockchain. If we check again on the state, we already have it marked as confirmed, and we got here a deposit. Why? Because I'm sending a transaction as a withdrawal, but the sender, the recipient, is also on our system. So we kind of detect both the withdrawal and then the deposit back into our system. So we get two operations. Okay? If we check, just to make sure that I've not you fooled, guys, if we check the MetaMask account, so this one has 999, the balance. Now it has minus 100. Actually, it is a bit less. If you see, MetaMask is rounding here, but because of why? The fees. We had to pay for the fees, so we do not actually have 899. We have a little less, and the other one has 1, so now it has 100. And if we now send back the, let's send it back. We are good guys. The guy mistakenly sent this fund, so we are gonna send them back because we are very nice. So we are here, we are sending the transaction. Let's switch back fast into our scan. And let's see if, oh, we just pick the same transaction as both the withdrawal and the deposit. Again, because we are sending from one of our accounts into some other account. And And if we go and fetch the operation, so we add 2 operations, now we get 4 operations total. Okay? So we are making withdrawals, we are detecting deposits, and we are, I have here an endpoint also to check the balance, but the balance will be easier, right? We are updating the balance on each transaction. And running out of time. So just as a wrap up about Anchorage Digital. So basically this is what we do in our day-to-day. So we integrate with blockchains. We actually provide what Anchorage is a platform for digital assets targeted at institutional investors, so banks, venture capitalists, fintechs, and what we provide is a custody service at heart, right? Being secure, bringing the security best practices of the industry into the custody of digital assets. So for example, this was created because our clients would have either a cold wallet, like a USB stick. I don't know how much of you are aware of those cold wallets, for example, kept in a safe, and they would only open the safe when they wanted to perform a transaction, or for example, have a phone just for that purpose, kept again away at the safe. Some also used more like multi-sig stuff, where each person had a part of the, basically a part of the private key, and they would gather all together in a safe space just to gather the pieces and to do the transaction. It was a real nightmare. So Anchorage Digital comes and fixes that problem, and on top of it, we provide a ton of added value, stuff that clients want to do on blockchains: governance, financing. We have a brokerage product. We have a finance product like lending and borrowing, and we solve problems for both crypto projects, for example, the Celo and Coin and Oasis. They are all blockchains. They have their foundation reserves, their reserves of crypto in our custody service. We also solve problems for infrastructure providers, what we would call fintechs, for example, Square and Visa, 2 big, giant payment processors. And of course, we heavily integrate with and heavily comply with all the regulators in the market to provide a safe, compliant, and up to standards, to security standards, to engineering standards, to keep digital assets, not other digital assets. And that's about it. I don't know. Don't know if we maybe have 1 or 2 minutes. I don't know, for questions if we have them. Kind of went a bit over time. Yeah. Sorry, I did not understood.
Okay, hello. Thank you. Yeah, the status that you have in your applications are status that you define, or these actual status that are in the blockchain. For example, confirm this belongs to the blockchain or it belongs to your application.
Yeah, so when we create the withdraw operation, we register that in our database. It's everything is in memory, but imagine in our database. But then everything, like the transaction being broadcasted, goes into the actual blockchain. The data is always kept in the blockchain. Okay, the data is all on that this Docker node that I showed you that is still running. So this is our node that holds the full blockchain data for us, the full ledger.
And if you set the not correct limits, your transaction can be living forever, waiting for a confirmation in the blockchain.
Yeah,
with Ethereum.
yeah, Yeah, basically it can. For the sake of managing here the space and memory, right, on these nodes, they normally have some sort of a timeout where they start dropping out stuff. But yeah, that's the main gist of it.
Okay, thank you.
I don't know. Any further questions?
So you need to sign those messages.
Yeah.
So I believe there is a registration process where you create your key pairs. Who is actually verifying this signature, and where there are the public keys for
Great question. Great question. Yeah. So basically, the way the Ethereum, there are other blockchains that do not do like this, but the way the Ethereum and, for example, Bitcoin blockchains work is anyone can create those keys. Basically, you are randomizing that public-private key pair, right? And with that, you derive your account address, and given that, you have an identity on the blockchain. Of course, you might say, if no one is validating this, couldn't I randomly generate accounts and try to match another account already existent on the network? You could, in theory, you could. But then, yeah, randomness, statistics, right? The probability is very, very low to have that collusion. You do have on some other blockchains where you have to make a certain transaction in the network in order to create an account. Basically, we are decoupling the account from the cryptographic material. So some are doing that. For example, Ethereum is also planning on doing that, on having only accounts within the blockchain, and you have that decoupled, and so you have an extra level of wiggle room, right? Yeah. I think there was also here a question. No.
Last question.
Yeah, you are always also free to reach me out in the venue today, or even reach out to me on my email here. Yeah.
So Gonçalo, this might be a dummy or newbie question because I'm quite new to this stuff, but it seemed like pretty easy to create an application. I know that there's a change upcoming in theory, which is the change from proof of work to proof of stake, right?
Yeah.
What would it change in writing this application? Like, would we still have a concept of base fees, tips, gas fees,
yeah.
or would it be completely different? I don't know.
Yeah.
Implementation.
Great question, and thanks for the comment. I love that you took something from here. So basically, what is changing in Ethereum is just the way the consensus is achieved. So it's changing from a proof of work algorithm into a proof of stake algorithm. So here it's just the monetary incentives that change. So instead of you spending electricity to validate the network, and for example, if you want to overcome the network and do bad stuff by yourself, you would have to have more computing power than half, like 51% of the network, right? More than half. Here, what changes is we change to a financial incentive. Okay, so in order for you to mine new blocks, it changes from mine to validate, the term validate. In order for you to validate new blocks, you have to put a stake, hence proof of stake. The stake is a monetary value that you have to put. I don't know, for example, imagine $100,000. That if you do not go together with the network, right, with the intended purpose of the network, if, for example, you are trying to include a bad transaction, if you're trying to be naughty, you will basically get slashed on that value, so you lose your money, okay? The fees are the same. If you send a transaction to the network, you are paying fees, so those which stake and are mining or validating blocks, they are getting back that fee, and they are increasing their pot, and yeah, and Some might discuss that it creates a bigger barrier of entry to meaningfully participating in the blockchain. It's a fair argument, right? For example, who here has $100,000 just to sit idle, just generating income, participating in the Ethereum network? Probably you have like a graphics card or whatever. You start saving for a graphics card and you start making a bit of a dent into. But some others would argue that yeah, with one graphics card, you aren't really going places. So it's kind of. It doesn't. It doesn't. The endpoint, the endpoints that the RPC API that we used, keeps the same. So yeah, doesn't change. The inner workings are kept the same. That's, for example, one of the reasons that people should not expect a meaningful reduction in fees, in the amount that you have to pay, because it's only like changing the consensus algorithm, right? It's not like scaling the network. It's not creating more bandwidth to include new transactions. So it doesn't really make much sense into the fees part. Okay, I think yeah. Feel free to reach out to me and to or to my colleagues also here. We have 2 more guys here. Feel free to reach out and to discuss stuff with us. Okay, thank you a lot for being here.